Bismillahirrahmanirrahim. Good afternoon, guys. Today we'll talk about the forces on the body by focus on the important things. At previous lecture, we was talking about the forces in the body, and we was talking about gravitation, electric, and nuclear force. Let me change the slide. Yes, same contents. When we was talking about the forces in body, gravitation force, electric force, nuclear force. Now we will focus on the forces on the body. It contains from three important forces. First one, fractional, static. The last one is dynamic force. We will illustrate all of them with important details. Let me start from the first one, fractional force. When we deal with some weight object and we'll try to pull it from point to point, this force will be clear. Here it refers to the force generated by two surfaces that contact and slide against each other. That means I will pull this object from a specific direction, and this object will start to resist me to reverse direction. This picture illustrates to us the specific fractional force. Here, the person start to pull it from this direction. The object illustrates it by the reverse direction. The equation is F, that's mean fraction force, equal the coefficient of fraction multiple normal force. Here, fractional force affecting and new factors affecting the fractional force. These forces are minorly affected by the surface, texture, and amount of force impelling them together. If an object is pushed against the surface, not flat, here the surface kind is very important. When it's be flat and when it's be not flat, that will be a big difference between them two situations, because the force will be different at these two equations. At first, when it's flat, the force will equal the weight, but when the surface it's not flat, that means the force will be not equal the weight. And we will take a look to these important information by then the fractional force will be increased and become more than the weight. Like I said before, when the surface is not flat, the force will be more than the weight. The force which we need to move this object from point to point must be more than the weight of this object. If an object is placed flat against the body, it's easier to change it from point to point. Why? Because no need to more force to make the force more than the weight. Here, just the force will equal the specific object's weight. Sorry. By that, the force will be the weight, like I said before. And the last thing, the angle, it's very important. Like we know, when put the object at the figure like that, at situation like that, sure the force which we need will different. By that, the angle and the position of the object affect the amount of fractional force. Here, the force which we need to change this object from point to point will be different. Specifically, when we try to take this object up. Why? Because another thing will resist us This thing is the gravitational force. Here, frictional force types: static, kinetic, rolling, sliding. The frictional here we want when we talking about when we focus on the dry that takes place between slide surfaces is classified as, like I said before, static, kinetic, rolling, sliding friction. Note, fluid friction, it is the friction that takes place between fluids and gases, not solid. Fluids and gases are termed at fluid friction. What does mean? That means we have friction force not just between two solid objects, solid bodies, but we have another kind from friction, can be between two gases or fluids. Here at these few slides, at first, I focus on the physics principles to friction, to force on body generally, and after that we will try to link these physics principles with medical field. Frictional force here, dry friction, describes the reaction between what? Between two solid bodies, like I said before, in contact when they are in motion. Kinetic friction, not static friction. Both static and kinetic friction is proportional to the normal force exerted between the solid bodies. Here, the other slides will focus on just the dry frictional force between solid. Okay, the last note, just to general information, to take a note, we have frictional force between not just two solid objects, but we have the same frictional between the gases and fluids. But the other slides will focus on the solid objects, the frictional between solid two objects, okay? Both static and kinetic friction is proportional to the normal force exerted between the solid bodies. It is a situation where the fluid provides resistance between two surfaces, this note related with the last one. If both the surfaces offer high resistance, then it is known as high viscous or greasy. When what? When both the surfaces offer high resistance, then it is known as high viscous or greasy. That's mean a high frictional force between these two solid objects, solid bodies. For example, to avoid here, we have example. I used it before, I think, like I remember at the first lecture between us, when I use it like example in, like I think in modeling, something like that. For example, to avoid creaking sounds from doors, we know when a little oil or the oil is disappear because using, these sounds will start to appear. We lubricate, that means put some oil with or a greasy thing between these two solid bodies, the door on the door hangings, which leads to the smooth functioning of door hangs. What does mean? That means the bad noise will disappear. Why? Because we use greasy thing. By that, the frictional force noise is disappear. Why? Because we don't have frictional force or the frictional force is decreased. Here, a physics example about when we have large block of ice are being pulled across a frozen lake. Here we have two solid objects The both of them are ice, but with different weight and size. The block of ice has a mass of 300 kilograms. It's a huge block of ice. The coefficient of friction, that's mean mu, between two ice surfaces, between this object and the lake, or this block ice and the lake, is small, equal 0.05. What is the force, that's mean fraction, that's mean F, that is acting on the block of ice? Always I advise my student to make them solution made from two important steps. The first one is the data. What I have, what the teacher wants from me, where and when I will put the question mark, and after that I can start to write my solution, to write my function, and keep going. Here I will start from data. What I have, mass, ice, block of ice, equal, its mass equal 300 kilogram. The mu of the coefficient of fraction, it's a small, like it's written there, equal 0.05. What is the fraction force between these two ice bodies? Solution, like I said before, we will write the equation F of fraction, the force of fraction, equal the coefficient of fraction, and we know it and the data, multiple the force at Newton, the normal force. But here we don't have the normal force result. By that, like we know, force with the Newton unit equal mass multiple acceleration. Here acceleration is equal 9.8 meter divided on second square. And by that, we have the mass equal 300 kilogram, like it's written there. By that, 300 kilogram multiple 9.8 meter divided on second square equal 2,940 Newton. Sorry, 2,940 multiple the coefficient, fraction coefficient, 0.05. I have 147 Newton. Here, let's start link this physical principle with the medical field. The advantage and disadvantage of fractional force, how we can walk safety around. Let's think about that. The disadvantage in our body, some disease of the body such as arthritis, it's a bad disease, kind of disease, increase the fraction in bone joints, like the doors example at the previous slides. Some disease because this fractional force, but between our joints. That's mean instead of the two solid objects at the last example here, the fractional force between the two bones ends at a specific joint. In our arms, our legs, at the legs it's more commonly increase the fraction in bone joints. The advantage, because the fractional force, we can walk around more safely. Fraction plays an important role when a person is walking to avoid sliding. Sliding can make to us some breaks in our bones. A force is transmitted from the foot, heel, specific at heel, like here, at this picture, a force is transmitted from the foot, specific at heel, to the ground. This the point transition. Force to the ground. The force can be resolved into two kinds of force we have, vertical and horizontal. At first will be vertical, the amount, the point, or let me say the second which we put our heels on the ground. After that, here it's vertical. To be horizontal, it's the second when we try to change or to move this heel to take another step. Here, normal and horizontal force. The vertical force N supplied by the service. Like I said before, the first step will be when put our heels on the ground, will be vertical force, and it's simple as N. After that, to take the second step will be the horizontal reaction compound, that's mean horizontal force. FH must be supplied by fractional force. By these two steps, the fractional force is important to make us walking safety. But normal walking, both of horizontal force and vertical force, decelerating make the or provide, how I can say that, decelerating, it's try to make our speed be less. Why? Because that has advantage to our body. I will say that at the last slide. Both of the horizontal force and normal force, vertical, decelerating have the same goal. That's mean to decelerating the foot and body. By that, the friction between the heel and the surface prevent the foot from slipping forward. When the foot leaves the ground, I mean, now I'm talking about the step, the second step, the fractional components of force prevent the foot from slipping backward, providing the force to accelerate the body forward. Has the same goal to prevent the slipping, to prevent some broken in our bones, and at the same time providing the force to accelerate, to increase the body forward, to take another step, to be ready, to be faster. It's some connect between the first one and second step. The F-net, that means the last result of F, or the summation between these two previous kinds, to static and kinetic fraction. When we have example like that, sure, when I walk on the smooth ground with angle equal 180 will be different from when I walking on the mountain, I don't know, with angle maybe equal more than 45. The specific point at my body center will be different. Here, let's come back to the details. Here, let me say the mu s, that's mean the coefficient of static fraction, mu k, to the kinetic fraction. If the body doesn't move, static. When don't have any move, the fractional force will equal coefficient multiple normal force, like I said before. Then, when we have a static fraction, F equal coefficient static or static coefficient multiple normal force. Here, N will not equal mass multiple acceleration anymore. The situation here is different. N will equal this specific amount, I mean mg cosine theta, not just mg. Here, the situation is more than 45, less than 20. By that, the static fractional force will equal static coefficient multiple mg cosine theta. By that, we know F net equal mg sine theta. Here, the body moving to this direction. By that, F net will equal mg sine theta minus static fraction or minus the kinetic fraction. What that's mean? That's mean here I will have two F net at static and F kinetic. Mg sine theta will be the same at these two functions and minus the static coefficient multiple mg cosine theta, but here will be at kinetic, will be kinetic coefficient. Here, we was talking about the fractional force. Here we will start to talk to illustrate the statics force. When objects are static, they are in a state of equilibrium. The summation of force must be zero in any direction. Here it's some important notes. And the summation of the torus about any axis also equals zero. Here the important information are started. Forces, muscles, and joints. Here we must at first have some information about physiology, because that I use this picture to illustrate the biceps, the triceps, and the moving, all of them contains from what is the muscle cells here, and how all of these moving, how all of these can take a weight more than them sizes, okay? Kettle muscles. The muscles which have small fibers with alternating dark and light bands. Let me explain these dark and light bands. Here I have light, here I have dark bands. By that, we say to them striated muscles here at all of the biceps and triceps. The fibers are smaller in diameter than a human hair. It's less than diameter of the human hair, but can be longer than them to few centimeters longer. The other muscles is called smooth muscles. Here I have two kinds of muscles at the biceps, triceps. First one is smooth muscles. Last one is here. The first one is smooth muscles. The fibers in the striated muscles connect to the tendons and from the bondins. Smooth muscles and striated muscles. Two kinds I have here. The striated muscles is connected with the tendons and bundles. Here, let's take a look. Where is the tendons? The tendons are here. It's something like banding between the bone and the muscles. Here, I have tendons here and here. It's a connection point between the bones and the muscles to these kinds. Here, muscles forces involving livers. What does mean livers? Livers, I mean, this picture can illustrate what livers means. For the body to be at rest, static, the sum of the forces acting on it in any direction, and the summation of the torques about any axis must be zero. Many of the muscles and bone systems of the body act as levers. It's important. At the next slides, we will try to illustrate what the connection between the levers and our lives, what's the connection between these few pictures and with our muscles work. Here, it's important because it will be different if I put it here or here or here. What will be different? The weight of this object maybe, or how much power I need to move this object. This will relate it to this triangle point. And here let's think about if this athlete woman, can use this weight, it's 15 kilogram, like I think, in this exercise. Can the same athlete woman to do this exercise? I don't think so. Here, levers are classified at three kinds we have. The most common is the third one. The least common is the first one. Here, first one. It's at specific point at our heads. Here, the triangle will be at the middle. Here, the weight, our weights, and here the muscles force. Second, at our heel, at our foots, yes. Here, the muscles force, the weight, and the triangle point. The third one is the most common one here, between biceps and the weight, triceps and the weight. Let's take more deeper look to these three situations, three kinds. What is the W here? The W is that's mean the weight, M the muscular force, and the most important thing, it's this triangle. That's mean the fulcrum point is most important thing at all the previous kinds. Fulcrum point. Where I put the triangle, I will make different situation, different weight, different efforts, different power will I need. The effort here, the main point to using the levers is to make the effort from small muscles be bigger than the load. Let me repeat that because that's important. By that, we make a great link between the physics principle and medical field. The main purpose to use the levers to make the efforts of these small muscles be bigger than the load. The biceps is closer to the fulcrum. Here, it's a specific information. Why? It's important. when the fulcrum point is near from the muscles, the specific muscles we will use, that will make the efforts to these small muscles be bigger than the load. This is the main point. Although this makes the mechanical advantage less than one. That's what we need. It means that the large movement of the arm are produced by only small contractions of the muscles. That means by this phenomena from small muscles, we can produce larger power to make, to change, to can take weights more than them offered, them power from point to point. Here, let's think about that. This athlete it's a athlete, deadlifter. If this deadlifter try to take this weight, what is the opportunity ratio to can do this exercise? I don't think so. The situation, the fulcrum point, let's think about that. It's right or not. It's possible to make this athlete to do this exercise. Can this athlete do this exercise and why? Here, other guys tried to do the same thing. These started to think about the fulcrum point. By that, all of them, here, if we take a look to distance between his hand to this weight, it's more than from this point to the heavier weight. Why? By that, the other one started to make the first distance be more and more the second. But the opportunity to all of these two persons to can take this exercise, let's think about that. Why the last one could do that? And at the same time, the weight was heavier. Here, the main point is it's focused and tried to calculate the fulcrum point, which one is the more appropriate fulcrum point. By that, this person left this distance, the first one, to be more and more and more the second one. That's mean make his body to be closer to the fulcrum point to give his muscles opportunity to can lift this heavy weight. That's mean he used his mind more than his muscles. The last one is the dynamic force when we throw out spear like that. What will change? Its direction, sure. What about its weight? What about its mass? What about its long? It's change its size, position, or direction. Size, that's mean it's long. Let's take a look about its mass. Maybe will change a little bit, sure. And after that, we will try to link that with our lives. The Newton's second law is, like we know, force equal mass multiple acceleration. Here, let's think about these two pictures. What it's happened to the spear? It's happened to all of these guys because at these two situations that we have acceleration. Suddenly acceleration. Acceleration effects. Acceleration can produce a number of effects such as an apparent increase or decrease in body weight, or not just the size, body weight, the long will change. Maybe if you used these games before, you feel about that. When the suddenly increasing, you feel some change, some pressure, clear pressure will be in your body. That will depend on the direction you are going. An apparent increase or decrease in body weight, change in internal hydrostatic pressure, distortion here is important. That's mean by increasing the velocity of these games more and more, that's mean some injury will have. Distortion of the elastic tissues of the body. That's mean it's dangerous because that's not all of the yanks can escape the, how I can say that, when you choose to be a pilot, you must escape, you must cross, you must take, you must do, I don't know what is the appropriate word, let me say, you must do a specific exercise. This exercise is related with the suddenly increasing acceleration. Any pilot need to cross this exercise. Why it's dangerous? Because some distortion of elastic tissue may be happen, and not all of the yanks can escape that. If the acceleration become large, may pull in various region of the body. That means some bloods will be at the same point at the various regions, and that will be dangerous. The location of the pulling depends upon the direction of the acceleration. Here at the last, it's very important if a person is accelerated here or his head first. The lack of blood flow to the brain can happen by that, can cases blackouts. B tissue can be distorted by acceleration, like I said before, if the forces are large, can be tearing can happen. Okay, that's it. Our lecture is done. It was the lecture number 2, forces on body. Thank you about things. You're listening, you're watching. Have a good day and see you on the next lecture. Let me end it.